Hi, this is Greg, part 4. Welcome back. This time we're going to talk about the reorder point, the point of inventory, the level of inventory that triggers a new order. Seen this a couple of times now, the overall questions and decisions being made in inventory management. When to place an order, how many, where should we locate inventory, and in what value-added state. This presentation, this video will be just about calculating the reorder point. So we'll see some of the math behind that and the thinking behind that as well. All right, here's the same problem we looked at in the EOQ video. It's the distributor who is buying HEPA air filters from a supplier. Remember the information there around period demand, ordering cost, etc. So some of these are relevant to the EOQ calculation, some are relevant to the reorder point calculation, some are relevant to both. Here's our challenge again. Determine an inventory policy around the HEPA filters for the distributor, and really that means calculating Q and R. Last time we were looking at Q, this time we're going to look at R. We're going to look at R a couple of ways. The first bullet there says we're going to look at it in two ways. A deterministic viewpoint, meaning we know everything about demand and lead time, and then a stochastic model where demand and lead time could vary. We still want to minimize costs, and we still would like to meet our service level obligations. And remember from the problem that the distributor had a desire of a 80% cycle service level. So again, we're going to address the when to order the R, and R is the trigger to place an order. At the very bottom there it says, what the reorder point is seeking to do is to minimize overall costs and meet your service level objectives in the face of the variability of customer demand and sometimes the demand or variability around supplier lead time. So things are supposed to show up at a certain date, sometimes they may be late. So we need to account for these sources of variation from customers and from suppliers in establishing and determining what the reorder point should be. So given all that information, I've grayed out again the things that are not relevant from the overall problem statement to the calculation of reorder point, just as we did in the EOQ video here. So we need to know period demand, we need to know the service level, and that's a policy statement from the distributor. They pick the 80. We need to know the lead time from suppliers, and we need to know any standard deviation. In this case, we only have standard deviation of demand, and looks like lead time is going to be fixed at 2 weeks. So in a deterministic scenario, and this is sort of to get the baseline case, it assumes that demand would be known and constant, and it assumes that lead times would be fixed. So here's the formula. R, the reorder point, is equal to the period demand during lead time, plus some safety stock to account for variability. Well, in the deterministic model, we don't have any safety stock. We don't have any need for safety stock because we know everything. It's known, it's fixed. So we sort of get rid of the safety stock bit. That goes to 0. So really the deterministic scenario says you should place an order when inventory reaches 120. And the reason is it takes 2 weeks to receive the order. Each week experiences 60 units of demand. That means as soon as it hits 120, immediately place the order. 2 weeks will go by, and as soon as you sell the last air filter, here comes your driver with a new order that we determined last time was going to be for 158 units. So let's take a look at the here's what this model looks like in a deterministic model. And so all the lines are straight. So the reorder point is what we're trying to calculate, but the rate of sales is known and constant, and then also the time between order placement and receipt of the order is going to be fixed at 2 weeks. So everything is known. There's no curves. There's no variation. That makes it nice and easy to say, oh, the reorder point should be 120. And that 120 then covers what that insert that says demand during lead time. We place it, and then 2 weeks later it shows up. And so we're covering with the reorder point demand during lead time. Now in this case, again, we know demand and we know lead time, so there's no need for any just-in-case inventory, any safety stock. We're going to now do the stochastic model, and that's going to allow us to incorporate a more realistic perspective where demand and or lead time could vary. So the formula is the same. It's still going to be DLT plus safety stock, and again, it's period demand times the lead time, the average lead time, plus safety stock. And the challenge here now is safety stock is going to be a more complicated endeavor than multiplying two numbers together, demand and lead time. So what's safety stock about? It's there again, just in case that demand is greater than average, greater than we perhaps expected. And also it accounts for the fact that we may have a supply interruption, so we can keep the factory running in a production situation, or make sure we have enough inventory in stock even though the truck didn't show up in the case of our given distributor. So here's what the model looks like. Again, it's the sawtooth model that we saw before. We're going to place an order. Some demand will occur, time will go by, then the lead time occurs, and then we're going to receive the order again, and then some more demand will happen, and there will be, again, demand during lead time. Now, in this case, lead time is going to be fixed at 2 weeks, but in other problems, the lead time could vary. It might be 2 weeks, but sometimes it's 1, sometimes it's 3, sometimes it's 5, because really bad stuff happened. And also demand could vary. So demand could be relatively stable. It could be slower than we had expected, but also demand could be greater than we had expected. So here's those two situations. Sort of the gold bar there is less demand than we expected. Maybe the turquoise was the regular, and the blue that's going below as well. Things got really, things were quite aggressive this period. We weren't expecting that, and guess what? We stocked out. Let's look at how this might work. So we need to understand, we're going to have to use our statistics here and go back to standard normal curve and all that kind of business to get this solved. And we use our standard normal curve again. So what do we have here? So the thick dashed line down the middle, that's the expected or average demand. And by the way, this is the same, it would work the same for lead time as well. So the average or expected demand, but sometimes it's going to be greater, and so there's a distribution here. There's a curve. That's what the turquoise is here. It's not just a fixed point. So sometimes demand will be greater than average. Sometimes demand will be less than average, and that's what variability is all about. That's what the standard deviation is trying to provide us or measure for us. So the safety stock is covering that amount where demand is going to be greater than we had expected. And so the cycle service level says, well, there could be a stock out. If the cycle service level in this case is 80%, then we're saying, you know what, 20% of the time we're not expecting to have inventory in stock when customers show up. Now this means, and what 20% are we talking about? The 20% is the 20% of those situations where demand was much greater than average. So that's what the distributor has elected to not fulfill. So in order to do this, you know what's coming next because you've had stats. We are going to have to use the standard normal lookup table and get to a z-score. So just here's another graphic of that the easy demand with the green dot, and the average demand with the yellow dot, and then the aggressive demand with the red dot. In this case, the demand was so great that it burned through the safety stock even. And that could be like our distributor with an only 80% service level. You know, it's not that unlikely that some of the situations demand could be greater. Perhaps it's a dust storm or smoke from forest fires. All right, so here's the calculation to make this happen. So the formula there in the red box is the entire formula. That's the generic formula that works for situations when just demand varies, when just lead time varies, or when both varies. So they're all incorporated there. So it looks the same as it did before. R is equal to DLT, that's the first two terms, average period demand times average lead time, 60 times 2. And now here's the just in case. So we let's look at the terms underneath the root sign right now. So the 2 is the lead time. We know that's the case. It's going to stay at 2 always. I'm not getting a pen, so we'll just have to keep it there. But there's the 2. We know the 10 is the standard deviation of demand. That's what the little d recommends. So we're not going to be squaring that because it is actually we are, because it's the variance in this situation. Okay, so same thing with average period demand at 60. Now in this case though, we didn't have any variance of lead time. So that term is 0. So it's going to, in our final solution, the 0 times 60 is going to turn into 0. There's no extra safety stock required because of lead time variance, because there is no lead time variance. It's going to be fixed at 2 weeks. All right, so now the only thing that's left here is the 0.84. Where did that come from? So I'm going to go forward here one time and get to the Z table or the Z-score lookup. So if you're doing this outside, you need to get a copy of the standard normal table or the Z table. You can find those on your using whatever your browser would be. In this case, remember the distributor had a desired service level of 80%. So you find inside the table, the values inside the table are the same as what's in the turquoise in the upper left-hand insert there. So once you find that number that you're looking for, 80%, could be 90%, 95, whatever, then you go up and over to find out what the appropriate Z-score is. To the left to get to the tenths, to the very top to get to the hundredths place. So in this case, we got the 0.84 is our Z-score. Let's go back and plug it in. So it's 120 as our reorder point. That's what it was in the deterministic model, plus some extra now. And the extra is going to turn out to be what? Another 12 units, 0.84 times 1414. So the demand variability here is causing us to hold an extra 12 units of inventory for the year. So what's our overall inventory policy? Now from the EOQ video, we knew that the how much to order was going to be 158 units. And now we just learned that in this case, well, this is still all the EOQ information from before. So it's 158. So our policy is going to be order 158 when the inventory level reaches 132. And now you can sort of see this represented graphically. And the pink at the bottom there is the safety stock, that extra 12 units. So I have another question for you. Well, what would happen if the organization wanted to raise their service level? Like, well, maybe they could advertise that and have a point of differentiation from their competitors this way. How much would that cost? So from a manager, we'd like to know that differential so we can help to be more informed to make the decision. So we're going to use the same formula, but in this case, we're going to have a table lookup at 95. So I'm going to not page up there. You can do that on your own through the presentation or go backwards on this video. But the internal number will show up to be 1.65. So it's going to be 1.6 on the left-hand side and then 0.05 on the very top. That's where it's quite close to the value of 0.95 on the inside of that table. So if we do the math, our new reorder point becomes 143 units. So our old reorder point was 132. So this is saying that we are going to raise our reorder point by 11 units. And really, this is safety stock. This is just in case stuff. So how much might that cost us per year? Well, how much does it cost to hold one item? That's 0.3 times 50. So multiply 11 by 15, that gives us the $165. So this policy change would cost $165 to go from 80 to 95% service level. Now, you might not think that's a big deal, but a distributor may hold several thousand items in inventory, and this sweeping policy change would be 165 times several thousand. So it's not a trivial number for an organization to deal with. Okay, that's how to calculate the reorder point given the possibility of variability in demand and variability in lead time. Cheers. Thanks.